So it's like 5 months.
You'll see it's like
That's fair. I just did it very in a very rudimentary way.
Sure. There you go.
But the first one that I did, I was just like, this coordinate is this one, this coordinate is this one, this coordinate is this one, for an entire 10 by 10.
Yeah, I was somewhere in between.
When you think about it, so that alignment was 125 points per problem.
Yeah.
Which is like each problem was weighted equally to like the previous one. Yeah,
Some half a homework assignment, almost, oh wait, or 2/3.
It's almost like 150, so almost an entire homework.
Almost. Oh yeah, you're right. I thought of the last one, and that's 250. Excuse me.
No, it was 200.
200.
Yeah, but like each problem 125 was almost an entire previous homework assignment.
Yeah.
It's like an hour each.
Yeah. So now that we're doing it in it'll be even easier. But my God, with the 8 a.m. section read, every time something goes wrong, it's like I do not know. I do not know.
I was wondering this morning, I crashed my computer, and it wouldn't restart. It's just like.
Oh, I cannot.
Yeah, I can hear you.
I was gonna say, because he makes the mistakes in your section, figures it out, and doesn't make them in
He
ours.
makes 4 mistakes per class in our section.
Oh,
She's just
In
tired.
ours, there's so many things he's like, no, I made this mistake in the earlier section.
That's
So-
fine.
So I have to make sure to not do it this time.
Yeah, that's our section.
Oh, you're in the 8 a.m. too?
Yes. It's not great, especially for homework turning out like for homework policy, because like I think you can get away with, say, if you don't turn it in by 8 a.m. if you run to his like office hours at like midday, you can drop it in his inbox. I think. You'd have to ask him about that. Because he mentioned something about that during solids last year. Yeah, I'm like, oh, neat. Like, it's like if you can't come to class but need to still drop it off, I'm not gonna penalize you for skipping class. I'll just penalize you if you don't turn it in.
Yeah, I don't plan on doing that, but.
I saw that too.
Do you see my notebook?
Alright,
Because I have my
everybody's
notebook.
here?
Hello.
Do you see it? Not this one, my other.
Oh.
No, I don't know, I feel like I'm losing students. I don't know. Are they okay? Do you have your project's teammate with you today? You're working on project 2A and 2B. Do you have a teammate with you today or? Oh yeah? Okay. Because today is the last day to drop the class or there. So you have to double check if your teammate is still registered for the class. Or all of a sudden the name is gone. Double check that. Okay. So suppose if you all of a sudden today realize that you are the only one working on the project 2A, you still need to do it anyways. I don't care. You have to turn it in by yourself. So please double check if your teammate is still registered for L1. Today is the last day. Okay. That's good news, huh?
Yeah.
Your teammates are surviving.
Long
Okay.
haul.
Let's just take a in-class attendance.
That's what happened to me for dynamics. Yeah,
Yeah, I
and
know.
they didn't tell me. They just stopped
No,
answering
don't worry
my
about it.
email right before a project was due.
Okay. All right, so let's just check updates today.
Much time.
There's a new update. Okay. So I really hesitated, didn't want to do this until the last minute, but I decided to share my code for project 2A. This is a task 1, semi-linear body. This is task 2 and 3, both included. Flow over non-lifting flow over circular cylinder. You're going to plot the streamline and also plot the CP distribution over the surface, and integrating from leading edge to trailing edge for the CP distribution to determine lift coefficient, and then you confirm it's 0. And you are going to compare against the theoretical results we derived, right? We actually gave you handouts, okay, for coefficient calculation based on the CP distribution. So a handout of unit B3B, B4B, those are very important handouts because you have to use it to complete your project 2A and both 2A and 2B. So this is my code, okay? So please, once again, this is just for your reference only. It's not your code, it's my code, it's copyrighted. So if you download and keep it as yours, okay, well, that's not good. Please don't do that. And then project 2B code, I decided. And I announced it here today, I'm not gonna give you it. Okay, so if you understand and if you build your own project 2A code, project 2B, simply you just add a circulation. Equation is different, that's the only difference between 2A and 2B. Okay? So you have to set all the basics done on 2A. And 2B is basically changing equation, that's it. I mean, if this is a perfect world, yes. Okay? So do your best to finish up project 2B. I'm going to show you how the project 2B code runs. I have a MATLAB right here. Okay? So this is my project 2B code, the cylinder lifting. I'm not going to share this code, period. You have to develop by yourself. Okay? So this is, like I said, MATLAB Live script. Do I write graph script? No. I use it because I cannot code it in MATLAB script so that you can copy. So I purposely developed in Live script. If you translate Live script into script, that's a skill. It deserves some points. So I don't care if you do it. Okay. So let's just run it, okay? So first of all, you're going to select the circulation. Obviously, project 2A, circulation 0, right? No lifting. And then project 2B, you're going to start adding circulation for the flow field. 3 different kinds of circulation. 3 pi, B infinity R, 4 pi, B infinity R, 5 pi, B infinity R. You have 3 patterns of stagnation points. So let's just run one at a time. I'm going to enter 0. This is going to be no spin. So what is the stagnation streamline?
0.
0, right? Okay. Let's plug in correct value. Okay. Minimum streamline, it could be any value, but I take default. Maximum streamline, it could be anything, but I take default. How many streamlines? 11. Okay. So if you do that, you're going to actually run this. Hey, this is a streamline plot for 0 circulation. Psi equal to 0 is stagnation streamline that actually follows the surface of the circular cylinder, represent the body. Okay? And then if you plot upper and lower surface CP distribution, obviously CP negative in positive y direction, you have to do this. CP equal to 1 stagnation point leading edge, CP equal to 1 stagnation point at the trailing edge, both upper and lower surface CP distribution exactly the same. So there's no difference of pressure upper and lower surface. So if you try to compute the area bounded by upper and lower surface, it is going to be 0. Theory also says must be 0. If you compute using numerical integration method out of those data points you computed, it's going to be CO calculated is 1.5443 times 10 to the minus 16. Very, very close to 0. But there's a small tiny errors. Okay? So percent error is infinity. Why? Because theory is 0. That's why. Something divided by 0 is infinity. So anyways. Okay. So suppose if you run it again, let's just add in circulation. So I'm going to have to start adding circulation 3 pi P infinity R. What is the stagnation streamline? Are you working on project 2B? It's still 0. Type in 0. Minimum, maximum, 11 streamlines. It's just a plot. Okay. So this is the streamline plot for the circulation 3 pi B infinity R, 2 stagnation points here and here. Psi equal to 0 still stagnation streamline because stagnation streamline is, if you have a stagnation point still on the surface of the circular cylinder, this is going to plot the circular cylinder shape, okay? Right? Because you still have stagnation point on the surface. So this is cycle to 0 line, actually go over the surface and flow away. This is now upper and lower surface CP plot. Now you can see upper surface is actually lower pressure, of course. Because CP negative upper surface means, hey, upper surface now you have a lower pressure distribution. Lower surface, you have a higher pressure distribution. So area bounded by those two upper and lower surface curve is going to be, what is it? Lift coefficient, CL, yes. So whatever you need to be doing in project 2A, 2B, you have to calculate area. How to do that? Well, you have to read the document. Okay, it's a numerical integration method, something called the trapezoidal integration. Okay, central difference scheme. Okay, do you understand? Okay, I hope so. And then, if you compute based on the data points given, CL calculated is 9.4186 and CL 30 is 9.4248. How did you get CL 30? Anybody? What is this 30? Go ahead.
I was wrong. No, it's 100% wrong what I was thinking.
Whoa. See, what's the CL 30? Anybody? CL is equal to, do you know that? CL equal to gamma over RB infinity. We derived it in last class. Hello, everybody. Are you doing it? So compared against the CL 30 is gamma circulation divided by R and B infinity. Okay, go ahead.
And that's because you selected the circulation you selected the circulation so then you can make that calculation.
That's right. Circulation you selected, in this case, is 4 pi B infinity R.
Right.
Divided by B infinity and R is 4 pi. That's it. This is 4 pi, right?
Yes.
No. 3 pi, sorry. 3 pi. 3 pi. That's 3 pi, right?
Yeah.
Yeah. That's what I'm talking about. That's the 3 pi. Anyway. So let's just run it again. This time, I'm going to select the circulation 2, which is 4 pi B infinity R. What is the stagnation streamline? Again, 0. Minus 2 to 7, 11 lines. So if you do such a thing, now you are going to plot. Here we go. So this is the streamline plot. Single stagnation point right here, theta equal to negative half pi. Psi equal to 0 still. Okay. This is going to flow over the surface of the circular cylinder, psi equal to 0. This is going to still show the circular cylinder shape because stagnation point is still on the surface of the circular cylinder. Okay. Now this is the CP plot on upper lower surface. Again, upper surface is going to be lower pressure than before, and then lower surface getting high pressure. So pressure difference is getting bigger, so you have bigger lift coefficient. Now CL calculated 12.55. CL 30 is 4 pi. That's 4 pi. 12.5664. Okay. Now next, last one. Select the circulation. This is 5 pi B infinity R. So what is the stagnation stream? My equations I go to?
I'm guessing 0.233.
0. Oh, you're guessing 0.233. Didn't you get this in your homework? Not yet. I hope you do that. 0.233. How did you get that? You have to find out in your homework.
Okay.
I'm not going to do it. Okay, you have to do it on your homework. Anyway, so please do your homework first before project. Okay. Anyway, so 0.233 psi equal to 0.233. Sounds like this is stagnation streamline. Okay. Minus 2, 7, 11 lines. Go ahead.
Is the maximum 3 for circulation?
Maximum could be anything. Eh? Circulation?
Yeah.
Circulation in this case is 5 pi B infinity R.
Yes.
This is circulation. So 3 is just a selection. Over. This 0 is a 0. 1 is 3 pi B infinity R. 2 is a 4 pi B infinity R. 5 pi B infinity. Well, just a selection, okay? I should have used like A, B, C, D, E.
Yeah.
Okay. Anyways, don't be confused for that kind of stuff. Okay. So this is circulation is 15.70. This is a stagnation streamline. psi equal to 0.233. How did you get that? Again, you have to do your homework. This is the stagnation point right here. It's no longer on the surface of the circular cylinder. So in order to represent circular cylinder, you have to literally plot the equation circle, put it on top of your flow field. That's the only way. Or you can plot psi equal to 0, because psi equal to 0 is circle. Okay, still circle. So anyways, you have to include both psi equal to 0.233 and also psi equal to 0 both. Then you can completely describe all the flow field streamlines. And then here is again CP plot upper lower surface. If you integrate, you can get CP calculated, and you compare against CL salary. CL salary in this case is 5 pi. Okay. So this is something you need to be doing. Project 2B, which is, when is the due? I don't know. After the Thanksgiving sometimes.
Okay.
That's good enough.
When do you want to know? When do you want to know? You don't want to know. You don't want to hear
No,
those.
I don't want to know.
You don't want to know? Okay. You
How about we
want to.
decide on
You
B4
just enjoy
first?
Thanksgiving, and after you come back, you all of a sudden you have to do this.
Cool.
Or I don't know. It's up to you. Go ahead. Question.
Yes, my question is, so for calculated, is it the worksheet
Yeah.
of flow of cylinder 2? For calculated, so like the formula for your calculated version?
Lift?
Yeah,
Yes.
not the theory. The theory is, yeah.
CL calculated is essentially this area, bounded by upper and lower surface,
Oh, so you have to calculate it from the graph.
from whatever your calculated data point,
Okay.
not the graph. I mean, how many data points do you have? It depends.
Okay.
You can plot the same CP distribution with fewer data points or more data points. Depending on number of data points, this calculation will change. In other words, if you have lower data points, this is going to introduce more errors.
Okay.
Because this is essentially numerical integration to determine this area bounded by upper and lower surface curves. It's called numerical integration trapezoidal method.
Yeah.
You have to read the document. Okay, please read the document. Right, project 2A document include that trapezoidal integration method. Okay? I hope. Right. Is that right? Am I
I think it's project 2B, but it is, it's not.
That's not the 2A. Okay, sorry.
Project
2B.
2A is just 0, so.
Yeah, because it's 0. You don't have to.
Yeah, that's, yeah.
All right.
Ah, okay, too bad.
Percent error.
Yeah.
Okay, so anyways, so that's the difference. Okay, one is numerical integration result. The other one is first simply gamma over RB infinity. That's the theoretical equation which we derived in last class. Any other question? So like I said, this is a project 2B code. I'm not going to provide the answer period. Okay, but I showed you in the class. Go ahead.
When are you thinking that project 2B should be due?
I don't know. It's negotiable.
Weeks from now.
Well,
Shouldn't we
2
decide?
weeks from now?
Shouldn't we decide on the due date for B4 first?
I guess so.
Yeah.
Because today, I hope I'm going to finish up
Because
B4.
B4 is kind of required.
And we also have.
And then, do you want to know the due dates of B4 homework? I guess,
I mean, we need.
Monday, maybe we talk about. Because Monday, everybody's online day. Still have a lecture, so we can discuss about it if you show up. You are part of the discussion on Monday. If you show up, one day. So let's talk about Monday, if you bring it up yet.
Okay.
So let's move on today. Finish up Unit B for today. That's what I want to do. So in last class, okay, we talked about, okay, so this is the lift coefficient. If you add the circulation to the flow of a circular cylinder, it is going to create the lift coefficient. Now, this is actually compared against the real flow. This is called Magnus effect. If you have a spinning circular cylinder, you're going to create the side force. I have a video. It's like a half entertainment video. I hate to show this, but let's take a look at it, okay? This is the Magnus effect video.
We're here at the Gordon Dam, and what we're going to do is demonstrate from the very top the effect of spin on a ball. So we're going to get a basketball and drop it from 140 meters up, one without spin and one with spin, and see what happens. All right, you guys do down the ball. Where's the curve small here? Yeah. Yeah, so it's crazy, just dropping it with no spin or anything like that, and as you could see, you know, that the ball was sort of doing a sway thing, so it wasn't going directly straight. It was pretty hard to predict where it's flying, so that was really cool. Ready? Whoa, look at that go!
So that's the main.
To get back in the water, do you?
So that's it. So this is, the rest is just entertainment. You're an engineer, you don't need to be entertained. Okay, so this is the Magnus effect of real flow field of a spinning versus non-spinning circular cylinder. You're going to actually numerically simulating those things. This is actually interestingly forming this baseline theory of circulation, theory of aerodynamics. Okay, so today starting point is there. Okay, so you did project 2A2B. You simulated the shape. Shape is a circular cylinder. Okay, so you have no choice. You have to use the circular cylinder shape. Now you have a choice of any circulation you can create and add it to the flow field. That is your project, okay? The shape, you have no control, but you can control the circulation. And then, as you know now, if you add more circulation, you're going to create more of it. So I guess, interestingly, if you want to create the airframe wing with a cross-section circular valve or something, if you spin more, it's going to create more of it. But you need more energy, of course. So now, let's talk about realistically, let's apply that to cross-section of a wing airfoil. So in this case, now you have no control over this is a circulation. You cannot control it. You can design this shape, and you can control the angle of attack, right? So whatever the shape you come up with, and then place it into some kind of angle of attack, it's going to actually determine the circulation of the flow field. Okay? Yes, we can. We can determine circulation of the flow field mathematically, as you did in Unit B1, B2, right? Some of the homework assignments. I forced you to do some very painful mathematical process of, okay, running through here, kind of thing, that actually determines circulation of the flow field. However, problem is, okay, here is the problem, okay. When you do, well, this is going to happen when you start using the software. Software you are going to pick up for the project 3, A and B, and then some of you are already using. What is the software you're using? Xflyer 5. That is actually called panel method. Panel method is the code that you're going to design your own shape using a bunch of straight edges to represent your shape. And each one of those straight edges is made up by a vortex. Okay, vortex, point vortex. You just the series, the series of point vortex arranged in a straight surface, and then you basically shape your body. So each one of those data points, how many number of data points to represent your shape? If you have 20 data points to represent the shape looks like this. All right? If you use 100 data points, it's going to be a little bit more smoother. If you use 1,000 data points, it's going to be very smooth. But still, anything is, it's a simulation. It's not exact shape. You're going to be representing the shape as cross as its own shape. It's not the super smooth surface anyway. If you really zoom in, it's just a series of straight edges creating smooth kind of looking surface. So anyways, that's called the panel method. Okay? So the shape is placed into incoming flow, and then you are going to set the condition that each one of those panels, the surface is going to be called the stagnation streamer. Okay? So this surface, the shape you design, is going to be stagnation streamline. So that means you are going to create stagnation point somewhere on the surface. Somewhere on the surface. That's the final message. Now, interestingly, if you do such a thing, the solution you receive is, okay, here's the solution. Then you go like, wait a minute, I don't think so, but this is the solution. In other words, saturation and then stagnation points have a very good relationship. Do you remember that? Let me just grab a pen. Because I saw a pen. So this is a circular cylinder. This is actual shape. Depending on the circulation, you are going to control two stagnation points, right? Flow gets in, flow gets out. Right? So depending on the circulation you are going to have two stagnation points. Stagnation point here, stagnation point here. Gets in, gets out. So the solution behaves like this. Okay. Do you have a question, Robert?
Yeah, the camera's not really facing.
I know. You don't need to. I don't need to record this. You just listen. Okay. Okay. Because this is the only thing I draw. So for your project, you have a control of circulation. As you change your circulation, you can control those two stagnation points. Right? That's what you did, right?
Yes.
Okay. So now, in realistically, X-Flyer 5 and other panel method, you are going to constrain those two stagnation points. As a result, you are going to control the realistic amount of circulation. That's it. It makes sense. It is actually quite important. Let me just turn the camera like Robert said. I still cannot see. Anyways. So let me repeat once again. This is your project. You control circulation to change the stagnation point. X-Flyer 5 and other panel method, you are going to constrain the realistic position of the stagnation point so that you are going to constrain the realistic value of circulation. What is the realistic location of stagnation point, you think? Trailing edge and somewhere in the leading edge.
Yes.
Right? Okay, so this is not right. This is something I want to see. So we need to add one more physics on top of the just the solution that you can get. So every single panel method actually have this physics added onto it. What kind of physics do you think it is? The key word, which is super important, guaranteed to show up on final exam. What is this physics you have to add to make this flow field more realistic? That is, realistically, oh, this is a stagnation point, here's a stagnation point. Flow field should be like this, right?
Viscosity?
Viscosity is completely ignored. For this. This is the panel method, still ideal flow. No. One physics that you have to add, very, very important terminology, guaranteed to show up on final exam.
Circulation.
Kuta condition. This is so important. Oh my goodness, I can't believe in it. Okay, whenever you use software, panel method-based software, you have to understand this. If you don't understand this, you are not qualified to use that software. Kuta condition is very, very important additional constraint so that, realistically speaking, flow needs to depart at the trailing edge smoothly. Okay? That's what the nature does. Okay? Have you ever seen flow field like this? No, right? Flow cannot turn like that and flow away. It's impossible. Only ideal flow can do it. But the real flow can never do such a thing. the real flow always depart at the trailing edge nicely and smoothly. Okay, do you know why? It's very difficult to explain why, but the nature does such a thing. Somebody discovered this is something the nature does. Somebody. Who's that somebody? Randall. Okay. So that's why this is a super important discovery. Could the condition, okay, the realistic flow field at the trailing edge flow need to depart smoothly. It's not going to depart like that. Okay. Could the condition must be added at the trailing edge. So let's just go back and carefully explain. I try to explain carefully. So here is the problem. This is ideal flow solution of the flow over a cross section of a wing without CUDA condition. In other words, okay, ideal flow solver, it doesn't care about the reality of the nature. So it is going to create any two arbitrary location as a stagnation point, okay, based on the shape and angle tag. Those two are the stagnation points because we're completely ignoring viscosity or anything else. So this is the solution. Is this correct? You go right, wait a minute. I don't think so. Because if I observe the real flow, it doesn't happen like that. The real flow always departs like that very smoothly at the trailing edge. So somehow this circulation computed needs to be adjusted to the realistic value, which is much, much less than gamma 1. If this is true, you just pitch up like this airplane and create lift coefficient 25. No, right? It's not happening. Right? So you have to somehow constrain it to the realistic value. Go ahead.
Yeah. So what if the flow field, let's say the flow field is a fan. What if it's like blowing on the wing?
Let's not talk about something real because it's confusing. Let's just talk about the solution. Make it more realistic. Okay? Go ahead.
So when you have flow separation?
Flow separation is a real flow.
Yeah.
We don't want to talk about it because this is still ideal flow. Flow never separates. That's why it allows to wrap around and flow away. Flow separation is an issue of viscosity. We are completely ignoring viscosity right now. Okay? So without viscosity, you can allow the flow field flowing like this, but this is not real. So let's just constrain this because circulation here is unrealistically too high. Let's adjust it with this condition. Let's not talk about boundary layer or viscosity. Viscosity needs to be added on later. Okay, that's additional things. This is still ideal flow. Okay. Okay. So I guess what you asked is also that's the real flow.
Okay.
Let's not confuse real flow to the ideal flow. We are talking about still ideal flow. So
this
now,
condition can only work for no viscosity, right?
this is no viscosity at all. Viscosity can be added later, boundary layer model, which is part of the software anyways. You can turn on boundary layer model. And that is going to be added onto this solution. But this solution, ideal flow itself, is something weird, isn't it? Already. So we have to add one more condition. That is called critical condition. So somebody actually said, well, this is not right. So what does nature actually adjust such a thing? Somebody observed. Who's somebody? Prandtl. Okay, Prandtl observed, okay, the real flow field. So this is interestingly, this is some kind of shape, cross-section of a wing. Yes. Then initially, nothing is moving. Let's say this is water tunnel or something. So burn at the time t equal to 0, you turn on the wind tunnel or water tunnel either way. Flow actually all of a sudden starts to happen. Then flow gets in, flow over it, flow away. If you observe very carefully, something happens. Okay? This is called starting vortex. So let's just take a look at the slow motion, one thing at a time. Flow gets in from left to right. By the way, today's lecture is probably priceless. You're probably not going to hear this kind of thing ever again in your lifetime, guaranteed. Okay? If you're paying huge amount of tuition, today is the day, the reason why you're paying tuition. Do you hear that? You have to recognize those kind of moments. So when you turn in the flow field, the flow gets in, right? Originally uniform flow. But because of the shape and angle of attack, obviously flow accelerates and also accelerates. And then, as you can imagine, you see this kind of thing actually starts happening. This is temporary stagnation point right here. And then this temporary stagnation point, okay, starts flowing downwards. Starts flowing. So this temporary stagnation point starts flowing, and right here, okay, right now, right here. So this thing is gonna shed off, okay, shed off, and then goes away. Then as a result, the excess amount of circulation from the flow field is all removed. So result is very smooth, at least departure at the trailing edge. Right.
How long does it take for the?
It's going to take very quickly. Let's take a video. Okay. So this is called starting vortex shedding, a phenomena that somebody discovered. So this is the nature's mechanism to remove excess amount of circulation of the flow field so that flow field circulation is adjusted. Okay, so that flow field becomes realistic, and the lift is not 25 with angle of attack 45 degrees. Kind of thing. Because you have to have a flow, smooth departure at the trailing edge. This is called starting vortex shedding. I'm going to share you a video today. This is probably the only time you're going to see this video. Okay, there's no audio. Let's take a look. This is Brando's video. So this is something called impulse flow field start. Flow field is not moving. All of a sudden you start up the flow field. Go ahead, take a look. Ah, something shed. This is called startup vortex shed. So this is the amount of circulation of a flow field which is not going to stay attached on the flow field itself. So this much circulation is removed at the very beginning of the flow field startup. So that as a result, upper and lower surface at the trailing edge flow departs very smoothly. Okay? Now, interesting thing is the other here. So this is, again, flow field is not moving. The body is actually moving. This is actually more realistic. This is a real flow field of airplane at the startup.
Let's pause.
Sorry. So this is the case that flow field is not moving at all. Body is moving. So this is actually a real airplane at the startup. So what happens here? Here we go. So you have startup vortex shed at the very beginning. So your flow field circulation is adjusted at the trailing edge. Okay. So that's what's going on here. This is the starting vortex shedding. So let's just take a look at what's going on here. Okay. So if you do not force the critical condition for your solution, okay. What happens is, this is your solution. Your solver arbitrarily creates two stagnation points based on the condition provided. Okay. But if you enforce the critical condition can be enforced mathematically. How would you do that? You are going to actually put either, if you have a finite angle at the trailing edge, you are going to set, this is velocity 0. So trailing edge is stagnation point. That's the condition of critical condition. But most of the cases that you have a trailing edge with a continuous angle change, it's called cusp trailing edge. This is actually very common design, right? Yeah. So if so, you cannot create the stagnation point here, but at least you're going to create the velocity v1, v2 equal to each other. So that if you force that kind of condition, you're going to force the velocity depart very smoothly at the trailing edge. May not have trailing edge become stagnation point. Stagnation point could be somewhere downstream, that's fine. Okay. But this is something called critical condition. Every single panel method code include this condition. Because this is going to adjust the amount of circulation of the flow field. Not only that is going to make the flow field more realistic, but it's going to be more accurate. Still, okay, still implicit, okay. Viscosity is still completely ignored, but the next step is in your X-Prior 5, you can turn on the viscosity. That is, viscous model is turned on, and then now you're going to simulate, okay, what kind of boundary layers has to happen. Initially, laminar flow, transition to turbulent, and then may separate, depending on the condition. Once the flow separates, parallel method stops computing. That's it, that's stop. Yeah. Okay, so that's how you compute this portion in X-Prior 5. This portion never happens unless you turn on viscosity. Okay, ideal flow, it just keeps going on and on. Okay, because it never separates the flow field. But even still, you have to have critical condition to have realistic result of ideal flow. So this much amount of vortex is removed at the very beginning, so that you're going to establish this type of flow field. That's what the nature does. And somebody observed it and then took a video. That's Prandtl. This is Prandtl's startup vortex.
How do you spell his name?
Huh?
How do you spell the person's name?
I believe
P-R-A-N.
GLT, I think.
silent T, Prandtl.
Yeah.
Ludwig. Ludwig Prandtl. So this is Ludwig Prandtl's starting up vortex shape. This is going to actually set up the CUDA condition. And the CUDA condition is going to adjust the proper amount of flow field circulation so that you can use this solver to predict the rift coefficient. But still, this is implicit. You have to turn on the viscosity if you want to simulate the surface pressure, surface boundary layer formation. Laminar transition to turbulent. Again, transition model need to somehow, it's so easy to make things complicated, right? Right, that's right. Anyway, but let's just understand the very, very basic grassroots level concept theory of circulation theory. Go ahead.
So I noticed that like in each of those videos, it was just the startup where it circulates.
Startup.
Yeah, but not in a constant.
No, once you start up, you are going to establish this flow field, steady state flow field. Right? And only at the beginning, you're going to adjust this circulation. Yeah. That's why it's called startup vortex. Chilling. Okay, right.
So with the CUDA condition for the cusp, it says the velocities are equal to each other. Does that mean the directions are also equal to each other?
That's right.
Like,
Parallel and then same exact magnitude. Yeah,
okay.
that's right. It's because you have a trailing edge continuously changing angle.
Yeah.
Okay. So parallel and equal to each other. That's how it makes smooth departure of the flow field at the trailing edge. Right. Okay. So this is important. So whenever you run X-Prior 5, here's the important thing. When you import airfoil data set, are you going to import as is into X-Prior 5? There's a problem. X over C, Y over C. Have you ever seen like an airfoil coordinate there?
Yeah.
This kind of thing. Yeah. Right. You can download it from anywhere. Problem. Trailing edge. X over C equal to 1. Need to be single location. That's clearly defined trailing edge. But most of the time when you import your data set, it is going to provide 2 data points, not quite X over C equal to 1, because it's cusp. Just continuously moving toward X equal to 1, but can never be there. If the trailing edge is often like this, okay, your code never runs. Guaranteed. Be careful when you do project 3. Are you aware of it? Are you aware of it? Okay, I hope so. So sometimes you have to literally create data points of trailing edge. X over C equal to 1. But that's it, here. Okay? Otherwise, your imported data just continuously going toward 1, but not quite. You have open trailing edge. Okay, if you import something like that into your panel method, it never runs. Because why? Because you can never do CUDA condition. Guaranteed it's not going to run. Be careful and be careful. Project 3. This is toward the final week, so I cannot help you. If you are not here today, not listening, not paying attention, it's your problem. I cannot help you. So that's one of those important things. Make sure you have a trailing edge well defined. Otherwise, you can never enforce CUDA condition. Period. Okay. Big hint. All right. So let's just conclude today's lecture by looking at last page. First example. Okay, so last page. So this is actually a very simple example problem. In other words, once you determine your saturation, can you determine lift? Or how much saturation you are producing if this much lift is produced? Okay, let's consider an airplane with a NACA airfoil with a code length 1 meter. The airplane's airspeed is 50 meters per second at the altitude 4 kilometers. The corresponding lift coefficient of the airfoil is CL equal to 0.8. Determine the lift per unit span, and also how much saturation do you have for this kind of flow field? Okay. It's actually a very simple deal. Okay. So let's say part A. 4 kilometer altitude. You're going to compute standard density at 4 kilometer standard, 0.8193 kilogram per cubic meter. This is density at the standard 4 kilometer altitude. Airspeed is 50 meters per second. Lift coefficient, you know, 0.8. This is probably from wind tunnel testing. So how much lift per unit span you're creating?
CL times 1/2 rho.
That's right, 1/2 rho v squared q times code length times CL. So, oops, 5 more minutes. Let's just finish up. 1/2 density 0.8193 kilogram cubic meters. Airspeed 50 meters per second square. Code length 1 meter. CL 0.8. So this actually gives you the how much lift per unit span you're producing, 819.3 newtons per meter. Okay.
That CL is a CL theory, right?
CL is like, you know, when you do a wind tunnel testing, you're going to determine CL, right? Lift coefficient. Is that your question?
Yeah, I thought it was the
CL
same as
is
the...
L prime Q infinity.
Oh, that's...
Right? Is this your question? Brother?
Yeah.
Yeah, this is the definition of CL. That's right. Okay. Part B, Kuta-Joukowski basically says that L prime is rho infinity, B infinity gamma. So this actually, interestingly, compute how much saturation do you have in order to produce this much lift per unit span. So just out of curiosity, I'm going to compute how much circulation do you have. 819.3 Newton per meter. Density is 0.8193 kilogram cubic meter. ASP 50 meter per second. So how much circulation do you actually have? 20 meters squared per second. This is actually circulation corresponding to lift coefficient 0.8. This is circulation. So your software actually does the exact opposite of this. Okay, you're going to design your shape and then place it into angle of attack with certain Reynolds number condition. The software computes the saturation with a CUDA condition imposed. If you can compute such a thing, you can determine lift coefficient of your design cross section of your airport, and that's what exactly software does. Complete opposite direction of this example problem. Okay. So this actually concludes unit B4, and then yeah, go ahead.
Yes. So question for page. What is it? Page 5. Why is I know you derived CL to be the other thing. Yeah, that yeah, right there.
Yeah.
You derived CL to be that, but what do you call that CL then?
This is the lift coefficient of the circular cylinder with a spin.
So this is lift coefficient with spin.
This is the lift coefficient of a circular cylinder with a circulation gamma.
Okay, and then the last
R
one.
is the radius.
Yeah, and then the other one is just lift coefficient.
Lift coefficient is always how much lift do you have per unit span, Q infinity C. C is, okay, in this case, C is 2 times radius, right? This is circular cylinder. It's the same thing. This is the original definition lift coefficient. This is the lift coefficient of the circular cylinder with the circulation gamma.
Okay.
Circular cylinder chord length is 2 times radius. Right? Right, okay. Any other question? Go back. Go back.
Thank you.
Go back to where?
The last page.
Last page. Yeah. Okay. Any other question? Okay. Have a wonderful weekend. We're gonna see you back on Monday. Everybody's online on Monday. Okay.
Yes, I only have one file.
This was a mess today.
It's not